Now we are going to discuss about direct and indirect bandgap semiconductors. Introduction. Semiconductors are of two types: direct bandgap semiconductor and indirect bandgap semiconductor. What is bandgap? Bandgap is the energy difference between the maxima of valence band and the minima of conduction band. Now, if you observe this picture carefully, this is an energy momentum diagram of a direct bandgap semiconductor. So, if you observe, the conduction band is above the valence band. So the difference in energy between the maximum of the valence band and the minimum of the conduction band is defined as the band gap. The minimal energy state in the conduction band and the maximal energy state in the valence band are each characterized by a certain crystal momentum k vector. Now we are going to discuss about direct band gap semiconductor and its properties. A direct band gap semiconductor is that in which the maximum energy level of the valence band aligns with the minimal energy level of the conduction band with respect to the momentum. Now observe this picture. This is an energy momentum diagram of direct bandgap semiconductor. If you observe this carefully, the maxima of the valence band and the minima of the conduction band are aligned with respect to the momentum vectors. That is, they are in the same position with respect to the momentum vector. With respect to the energy vector, the conduction band is above the valence band, and that difference is given to us by the band gap. So, as the conduction and the valence bands are aligned with respect to momentum, a direct recombination takes place with the release of energy difference between the recombining particles. Since a direct recombination takes place, the probability of recombination is high, and hence the efficiency factor of direct bandgap semiconductor is higher. These properties makes the direct bandgap semiconductors useful as sources in modern day life. In a direct bandgap semiconductor, if a photon of energy E, where E is the bandgap energy, is given, then electrons present in the valence band jump to the conduction band, creating a hole in the valence band. So an electron-hole pair is created when an energy E is given to a direct bandgap semiconductor. Gallium arsenide is a famous direct bandgap semiconductor. Now, if we observe the above diagram carefully, direct bandgap semiconductor The if carefully, the above diagram indicates how the actual electron states are equally spaced in the k-space, which means that the density of states depends on the slope of the Ek curve. Now that we have discussed about direct bandgap semiconductors and their properties, we move on to indirect bandgap semiconductors and its properties. An indirect bandgap semiconductor is that in which the maximum energy level of the valence band is misaligned with the minimal energy level of the conduction band with respect to the momentum. For a better understanding, observe this picture. In this picture, the conduction band has been displaced by some amount with respect to the momentum vector. So the valence band and conduction band are not aligned. This causes some problems in the indirect bandgap semiconductor. In case of indirect bandgap semiconductor, due to relative difference in the momentum between the conduction and the valence band, first the momentum is conserved by release of energy, and only after both the momenta align themselves, a recombination occurs aligned with the release of energy. Since the conduction and the valence bands are not aligned with respect to momentum, so the radioactive recombination requires conserving momentum firstly. So the probability of recombination is low. Eventually, the efficiency factor of an indirect bandgap semiconductor also drops and is pretty low. Silicon and germanium are famous indirect bandgap semiconductors. Thank you.